All right, so I want to start by telling you about a vulnerability on the web called cross-site scripting. And hopefully last time you learned about cookies, which are a mechanism that your browser uses to keep track of some information and send it back to the web server when needed. Widely used, for instance, by web servers to keep track of who you are. So when it gets multiple requests from your web browser, it knows it's from the same web browser as from you. Cookies are used for authentication. You enter your username and password, then the web server knows that's you, and then it remembers with that cookie that any other requests from that same browser, meaning any other requests with that same cookie, are also from you. And you saw cross-site request forgery last time, I think. And today we're going to talk about cross-site scripting. And I want to start off with an analogy, because I like analogies. Maybe this one is a little weird, but let's start with it. Let's go with it. I want you to imagine that I am at I'm at a bar. It's Friday evening, and at the bar I see my worst enemy. We'll call her Emma. Let's not talk about what's happened between us. There's some beef. It doesn't really matter. And I happen to see another person there who I know is Emma's private banker. Okay? And I go to Emma and I give her, I write down on a piece of paper, I give her a note and I say, would you pass this on to that guy over there? And that guy over there is her private banker. And what I've actually written on that note is, I'd like to make a payment of $1,000 to Dave Wagner. Would you please put that in place, Monday morning for me? Okay, so let's say whatever way I convince Emma to go give this note to the banker. I tell her, I don't know, it's a surprise for him. Would you play along? He's going to love it. And she does. And her private banker receives the note. What's the banker going to do? Maybe. Possibly. Arrange a transaction to give $1,000 to me, because the banker doesn't realize that this note is actually from me. He just sees Emma giving him a note, and maybe he's eager to do whatever his client's wishes are. Okay, a little bit unrealistic, but of the vulnerabilities you've seen in this class, what one does that most resemble? Any? Yeah? CS or FA? Okay, tell me more about what you're thinking, if you would. Are you willing? You get the person to send something. In this case, sending something is giving a note. Who plays the role of the web server in this little story? The banker. And who plays the role of the web browser that's getting attacked, or the user that's getting attacked? Emma, my enemy. Okay. So it's like that. If that trick actually worked, that would be same as a cross-site request forgery. The difference is that in practice, people are kind of, people are people and have common sense and don't necessarily play along and just do what they're told. But computers are computers and will just mechanically do whatever they're told if that's what the software tells them to do. And so this kind of a trick can be 100% successful against computers if they're not set up to defend against it. Okay. So that's cross-site request forgery. Are you with me? Okay. I want to change it up now. I want to imagine we're at a bar and I still have it out for Emma, and whatever. I've got another scheme, and I notice sitting over there in the corner is this enormous dude. He is huge. He is jacked. His muscles have got muscles. He's in a leather jacket. He looks tough. You do not want to mess with him. Let's give him a name. The Hulk. Okay. This time I give Emma a slip of paper and tell her, hey, it says it's his birthday party. I'm making a surprise. Would you give him this note? He's going to love it. But written on the note is, you dress funny and your mother smells of elderberries. Okay, what's going to happen when Emma gives him the note? I don't know, maybe nothing good. Maybe he's to swing at her or something, right? Okay, that's a scenario. Let me change it up a little bit more. I want you to imagine now that I give Emma a note, and again, I'm going to try to convince her to give it to the Hulk. But this time written on the note is something that says, hey, I'm trying to impress this other girl. Would you play along just to help me out here? Would you tell me, you better buy me a drink or else, or I'm going to level you. So she gives this note to the Hulk, and what does the Hulk say? Oh, you better buy me a drink or else I'm going to level you. And Emma doesn't know that this is what's going on, and is like, oh my gosh, and goes and buys the Hulk a drink. Okay, that's a scenario for you. Pretty implausible with people. That's what cross-site scripting is going to be like. Okay, so cross-site scripting, we're trying to get a web browser or a victim user, that's Emma, to send something to a website, the Hulk, who's going to send something back, who's going to say, hey, you better buy me a drink, that Emma, the browser, is going to then act on, follow. And in acting on or following that is going to, harm Emma. Okay. So that's cross-site scripting, but let me show you it. Let me show you what that means in the context of the web. Just to give you a little bit of context, why am I teaching you cross-site scripting? First of all, I think it's an interesting example of a broad class of vulnerabilities that happens not just in the web, but multiple contexts. When you see it, once you learn to recognize this class of vulnerability, you'll see it everywhere. But second of all, it's possibly the most common security vulnerability, type of security vulnerability, in software, according to one rating of reported security vulnerabilities weighted by how serious the impact they are. Just super, super common, really easy mistake to make. So you should know about this so you know how to defend against it. And to give you a little bit of background, when you have multiple websites, the idea of your web browser is it's supposed to allow you to browse multiple websites even if you don't trust them. You could go see the CAPTCHAsforum.com. I love it. Great stuff. And that it's safe for me to do that even if the owner of the CAPTCHAsforum.com is malicious and trying to attack me and get access to my bank account, and even if I've got another web browser window open logged in with my bank.com. So it's the browser's job to keep those two separate. And part of the way it does that is with this same origin policy, which says that stuff running in the browser window from the CAPTCHAsforum.com, like JavaScript or any other thing happening there, can't really access the data of stuff in the window from bank.com. Okay, so there's some separation the browser enforces. JavaScript that comes from the CAPTCHAsforum.com can read and write content in that same browser window from that same domain, but not from other domains. So the separation is by domain. Origin is another word for domain on the web. In your web browser supports JavaScript. JavaScript's just a programming language. The web server can send your browser JavaScript, and your browser will automatically run it. Many web pages contain this code, and this JavaScript code can access, read, and write, and modify all of the HTML content on that page, can send other requests to the same web server. Super common for websites to use this. Really like critical to the functioning of the web. And the way that you include JavaScript in a web page in HTML is using a script tag. So you put these angle brackets script, and then you put the JavaScript code, and then you put the angle brackets close script. Slash means close, end of the script region. So everything between those two tags is treated by the web browser as JavaScript code and is run as soon as this page is loaded. And there's lots of stuff that JavaScript code can do. And if you call the alert function, what it does is it pops up a little pop-up window. This is so not important, but it's just a standard way that people often use to debug JavaScript. It's like the equivalent of print line, like a print statement for print debugging, where you print out some stuff as the code goes, or see if this point of your code is ever executed. Put a print statement in here that says, haha, I got here. Same deal. One way to tell whether JavaScript is ever running is to put an alert thing that says, haha, this JavaScript ran. Okay. And I'm going to use that to like demonstrate vulnerabilities where like the attacker is going to show that their JavaScript is running by pop-up box. But actually that's no attacker actually cares about popping up a pop-up box. They want to like steal your bank password or something. But if they can run JavaScript that pops up a pop-up box, they'll also be able to do stuff like steal your password. So it'll be like an easy to recognize demonstration that the attacker can do bad stuff. Okay. So I want to look at some sample code that might be part of a web server that's providing some website. So the top up there is some code that might be part of a website. So this code, if the browser sends a request, it figures out what to do with that request, prepares an HTML web page to show in response, constructs that HTML page on the fly, and whatever is output with this printf is the HTML that's sent to the browser. Okay? So if you open a browser and you enter in this URL, which vulnerable.com is running the code up top shown there, then it'll run that function. And in a URL, you can specify parameters. Question mark means some parameters. It's like a key value store, like in a hash map of these things. The name of the parameter, equals sign, the value of the parameter. In this case, the value is evanbot. And this code, the first line, look up the value of that parameter. So it'll set the local variable name to be equal to the string evanbot when it's processing the request for this URL. And then it'll print what's shown down here, HTML. This HTML is what the website sends to your browser, and then your browser will display the web page corresponding to that HTML. So here, the web server has responded with a very simple HTML page that contains some content. Hello, evanbot. Super like simple, boring, like kind of hello world of web programming. I know this is a lot of setup, but I'm getting to what the cross-site scripting vulnerability is. That's the setup. Before I dive into the vulnerability, I want to take a break for like questions. How are you with me so far? Where have I lost you on? What could I clarify or explain better? Yeah. Uh-huh. What causes that that function to be run? Um, Somewhere there's some configuration or some code that has maintains a mapping that says if there's an access to the page hello, if the start of the path is hello, then run that particular function. I haven't shown that configuration. It's called a route, I think, often. How we doing? I just talked a whole lot. I want to give you a chance to talk at me. Yeah. Yes, great. If I changed EvanBot in the URL to Davy, then what would come back in the response is Davy. Could I use that to do something maliciously on the website? Absolutely, and that's right about what I'm about to show you. Do you want to make a suggestion, or do you want to let me go on and like show you? I'm good either way. You said there's some JavaScript in the URL. There's not actually any JavaScript in this URL, and there's not any JavaScript in this HTML page because there's no script tag. But I like where you're going. We could try to get some JavaScript in there, and that's what we're going to do. Yeah.
Queries inside of that, like the response or whatever variable you have there.
Could I put some shell code in there?
It's like, is there a way? Because right here it says like the assuming it's like a query, it's like the hello, and that's what calls that function.
Yeah.
Could we put something in there that calls a different function?
Could there be, okay, could we change the way the web server works so it calls a different function? Like a goodbye instead of hello. Usually no. Usually in the code, I haven't shown you that code, so I'm sorry, there's no way you would know this. But in most web servers, they have hard-coded some central code that looks at the URL, and if it says hello, then call the hello function, and if it says goodbye, call the goodbye function, and that's hard-coded in the web server's code. An attacker's not going to be able to change the web server's code, so they're not going to be able to change which function gets invoked if the page that's visited is hello. And usually that code that figures out what page is being visited, it ignores everything after the question mark. It like removes everything after the question mark and puts that in a separate hash map. So that's not going to affect which function gets called. Yeah.
There's a string or like a string format or format string vulnerability with the fact, like, let's say we didn't give the input into the ender. It was just the only input was, for example, like
Aha.
would it be the web servers?
Yeah, if there was a format string vulnerability here, could we attack this? Absolutely, absolutely. If there was a format string vulnerability, if that was like C code and it had printf name instead of a %s and name is a separate. If there was a format string vulnerability, then you could totally attack this. What you would be doing, that would be a vulnerability in the web server code, a memory safety vulnerability, that an attacker could send a malicious URL and like overwrite RIPs in the web server and start to like get the web server running malicious code. Absolutely. Absolutely. For instance, if we wrote web servers in C or C++ and they had memory safety vulnerabilities, you could hack into the web server that way. But that, oh, hello, bird friend. That is really uncommon because we've kind of learned that C and C++ is not safe, that we should use memory safe languages. And most web servers are not written in C or C++. They're written in like Java or Python or PHP, all of which are memory safe languages. And so you're unlikely to have a memory safety vulnerability in the web server. So it's less common to see vulnerabilities that allow an attacker to directly take control of the web server. Instead, what we have to do is something that causes the web server to send something back to the browser that causes the browser to do something harmful. It's like this indirect thing. Okay, so let me show you the attack. I've set things up enough, I think. Let me point out an observation. If what's in the URL here has some markup tags, like in this case, I put a B tag, that's short for bold, then this code is just going to copy that, whatever it is, straight into the HTML page, right? So the HTML page, when it's rendered by the browser, will now show EvanBot in bold. Good? Okay. And it doesn't have to be just bold. It could be italics or really big font. It could be an image tag here, and then you would get hello and then some image. That'd be kind of cool. But even more than that, it can be any HTML tags. And so we can construct a URL that contains a script tag and then some JavaScript code and then another script tag. And as far as the web server is concerned, this code is for the web server, has no idea what the format is. It just copies blindly whatever's given into the HTML that it returns. So the HTML that's returned will now have this markup for a script tag. And when the browser renders that, now the browser sees a script tag, says, oh, there's some JavaScript code in this web page. I better execute it. And it executes this line here, and this line of code pops up a pop-up box. Yeah. This is called XSS. It's short for cross-site scripting because we all know that cross starts with an X. We're cool and we spell things differently. And don't worry yet about why it's called cross-site scripting, but at least you can see with the scripting part, I haven't really told you why it's a vulnerability or why it's an attack or why anyone's harmed. But I'm just kind of noting some peculiar aspects of this code that maybe is not what the developer was anticipating or intended. Yeah? This is not in any way a format string vulnerability. Even though I've shown fprintf, this string could have been combined in any other way, like string concatenation or something like that. It's not specific to fprintf. It has nothing to do with format strings. Yeah.
Is on the web browser side, does it parse it, or does it parse what it's supposed to be showing on based on the tags individually one by one as it reads them? Or
Yeah.
how does it know what to do when?
How does a web browser know what to do when? You can think of it as the web browser gets this HTML page. Think of it getting this entire document, the entire string, the entire file of this HTML, and then it parses it into some has a context-free grammar, and it makes a parse tree if you know what that is. It finds all of these tags and finds which parts are within the nesting structure, and then for every it displays that appropriately. If there's a bold, it displays that, then it displays that in bold. And for every script tag, everything with it nested within a script tag, it treats as code and starts up the interpreter and immediately runs that as soon as the web page is loaded. Now, actually, web browsers do something clever where when you load a page, the web server might be really long page and might send you stuff and might take a while for it all to arrive. And so they actually start, even before they've gotten the whole thing, they start parsing the beginning and start displaying the beginning, but don't worry about that. That's not important for this. I just lost you, I see. I'm sorry. I shouldn't have even said that.
Would it be possible for it to say, or for it to give the like tag script and then that do something to change the rest of the response?
If there's a script tag in there, you're asking if that might change what the JavaScript code might do when it runs, or how it might affect the interpretation of the rest of the.
Well, the interpretation.
Okay, yes. For instance, if there was the URL contains open script tag alert and then didn't have any closed script tag, then here it would contain open script tag alert. There'd be no close. And then the rest of the HTML document would all be interpreted by the browser as JavaScript. Because the browser just gets one file. It doesn't know where the boundaries were intended to be, so it just interprets it as a file. So if you put malformed HTML into the parameter with this, then the web page that comes out of this might look weird. Yeah. If there's no closing tag, your browser will try to do something to like make up for the syntax error. Browsers try really hard to find some interpretation, even if it's not like syntactically valid. Like, for instance, maybe it'll treat the rest of the document as being all JavaScript or something crazy like that. They'll do something unexpected. You don't need to know that because the attack doesn't rely on that. Okay, so this is an odd feature of this code, but not yet like a security vulnerability or an attack. Can notice, though, there is a little bit of a problem here. The name was probably intended to just be as text that appears on the web page. But in this case, we've created a URL that causes the name to actually be interpreted by the browser as like control data, as like markup tags and code and so on, not just data like a name, which is a sign, a warning sign. And this JavaScript code could be anything. It doesn't have to be limited to just alert. For instance, it would be possible to write some JavaScript code here that does something malicious. Like one thing that would be done, the JavaScript could do is read the session cookies for the current web page and then send them to davewagner.com. That's something that JavaScript can do. Your browser will let JavaScript here read session cookies for the website that's being displayed, because JavaScript can do anything with the same website, that it's displaying, and can send that anywhere. So this is starting to look like a security vulnerability. I could construct a URL so that if I load it in my browser, sends my session cookies to davewagner.com. And if you loaded it in your browser, it would send your session cookies to davewagner.com. So far, not much of a security vulnerability. If I construct this crazy URL and then I load it in my browser, I just shot myself in the foot. I mean, come on, don't shoot myself in the foot. Like, what's the harm there? I had to deliberately do it, and then I can like deliberately shoot myself in the foot. Doesn't seem like anything very serious yet, but it actually is serious. Anyone want to give me an idea why this might be more serious? It's not just harm myself, a way that I can harm myself, but it's a way that I can harm others. How could I harm others? Yeah? Like a phishing attack? Do you want to say more? Yes, totally. Yeah. Yeah, maybe. So maybe if I can get you to load this URL in your browser, It'll send your cookies to davewagner.com, and now I can log in as you. So I just have to get you to load this URL in your browser. How do I do that? I have to come up with some way to kind of scam you or con you into doing that. Like I send you an email, it looks like it's from Twitter, and that looks like it's a link to Twitter, but it's actually not. It's this crazy malicious URL. So that's the security vulnerability. The security vulnerability is not that I can harm myself, but that I can, if I can trick you into loading a URL, that causes you to harm yourself. But you're not aware that you're harming yourself. I know I'm like laying a lot on you, so stop me and help me get you unstuck where I've lost you. Because if I were listening, I would be lost right now.
Would that like be able to like just use that on another device?
You would. It's amazing.
It like such does it allow that if you just like
On many websites, most websites by default, the standard way of doing things, unless the website does something extra. If I take session cookies from my web browser and I give them to you, you put them in your browser, you load the same website I was logged into, you're going to be logged in as me.
at all?
It's really bad. Yeah, it's like the same as reading a password. Like, wow, we really are getting a visitation here, aren't we? This is so awesome. I wish I could help that poor bird find a way out. Okay, yes, like if you got my password, then you could, like my Amazon password, you could log into my Amazon account and order stuff and on my stored credit card. Same thing, if I looked up if I logged into Amazon on my web browser, got my session cookies and gave them to you, you could load those session cookies into your web browser, make requests to Amazon, and the Amazon website would think that it's me. You'd be logged in as me, and you could make orders and it would get charged to my credit card. And why is that? It's because like web servers have no other option. They're designed to be stateless, like basically stateless. They receive a request, they do something with it. They receive another request, they do something with it. They forget everything about it. And so how do they know who's sending this request? It could be from anyone. The only way they know is by the cookies. And they have a database that keeps track of, for this cookie, I know Dave Wagner has logged in and provided his password. For that cookie, no one's logged in yet.
Like sensitive data if they're encrypted.
Usually cookies don't have any sensitive data in them. They're just a unique ID to make sure that I get a different number in my cookie than yours.
Like any token set, like if you could read that.
Yeah, so if you could read the session cookie that my web browser has for Amazon.com, that's really bad. You're now, yeah, buy stuff on my credit card. Totally. Okay. Now I should give you the more detailed answer, which is some websites know about this threat that I'm talking about, and they have extra defenses to say, oh, you're using this cookie from a totally different IP address, and maybe that's fraud, and we might make you log in again. But they can't do it too often because when you use your cell phone, it's constantly getting new IP addresses. So it's really common for web servers to see requests coming from different IP addresses with the same cookie, and it's nothing malicious about that. Yeah, okay. Question? Yeah. All right, and there's nothing here about fprintf. This doesn't have to be fprintf. I showed an example of code with fprintf, but there's nothing specific to fprintf here. If this code was written using string concatenation, it would have exactly the same vulnerability. Doesn't really matter how this code is written. What matters is that this code is echoing whatever is in the URL directly, byte for byte into the HTML response. Okay, so this is called cross-site scripting, XSS for short. And the idea is the attacker is going to add malicious JavaScript to a legitimate website. How does the attacker do that? The attacker probably doesn't have access to edit the web pages directly. The attacker doesn't have admin access on that website. So they're going to exploit a bug in the code, this echoing stuff directly into the HTML response to have the effect of adding malicious JavaScript to the website. It might be for everyone or it might be just for you. Okay. So cross-site scripting is when an attacker can introduce or inject JavaScript into websites that are viewed by other users. That's the cross-site part. And there's two main types of cross-site scripting. One's called stored XSS and one called reflected XSS. Yes, question.
Cover this vulnerability by making sure that the input isn't ever script, like parsing the input.
Oh, you're thinking about defenses. Love it. We're going to get to that. So hold on to that. Save that. Think about how to defend against it in the back of your mind. There's a bunch of defenses. Some of them are better than others. Love it. I feel like we've been just spending forever and ages on this thing. Do we need a break? Could we use a break? Would a break be good? How many would like a break right now? Ish. How many are game to keep going? All right, we got energy today. I love it. So let's keep going then. Stored XSS and reflected XSS. Let me tell you how each of these work. Stored XSS is when the attacker does something and they've had the effect of editing the web page, like for everyone. There's now JavaScript on this web page permanently for everybody who visits that web page. Okay, and a very simple example would be a Facebook page. Like I put an update message on my Facebook. I don't even know how to use Facebook, sorry. But like, I guess I could post a message that says like, yo, I just got back from Taiwan, it was awesome. And then everybody who visits my Facebook page will see, yo, I just got back from Taiwan, it was awesome. And so now the attack would be, instead of putting, yo, I just got back from Taiwan, I could instead put, yo, comma, open script tag, some JavaScript code, close script tag. And if Facebook was naive, that might get echoed directly into the web page, you know, my web page, my Facebook page, that when you visit my Facebook page, now that JavaScript is included and your browser runs that JavaScript code. Why would that be bad? What could I do that would be bad? How could I harm you if you were like visiting my Facebook page? I got you. I want to see if anybody who hasn't raised their hand wants to take a try at this. I promise a no judgment zone. What's that? What is bad? How could I cause harm to you by writing a status message like this with script tags and so on that like causes JavaScript to run in your browser? Why is that bad from a security perspective? Does it matter? It does matter. It's bad. Yeah? La! Exactly. Yeah, it's the same deal. I could write some JavaScript code so that when it runs on your browser, that JavaScript code reads the Facebook cookies in your browser and sends it to davewagner.com. And now I've got your browser's cookies for Facebook, which means I can log into your Facebook account and see all those secret messages you're sending each other about, man, that lecture was so lame. I just wanted to be home, or whatever it is you're sending. So that is stored XSS because I have put something on that page. I have somehow gotten Facebook to add something to this page that it sends to everybody, no matter who visits that Facebook page, the Facebook page for me, they get the JavaScript. So I've kind of conned Facebook into putting some JavaScript, some malicious JavaScript on their website that they never would have like deliberately agreed to, but their code was willing to add anything, so I was able to do it. Yeah. How does that look in JavaScript code? There is a global variable that has your cookies. I forget what it is. It's like document.cookies or something like that. So JavaScript can read from that global variables. There's the cookies. And then there's a function call that JavaScript can make to send a request to a website. I think it's called fetch. And it can fetch any URL. And so what the attack might do is it might concatenate davewagner.com/ and then concatenate document.cookies to get a URL that will go to davewagner.com, and then after that in the URL has the cookies. And then the JavaScript will call fetch on that URL. And now davewagner.com web server could be set up to log all the requests it ever gets, and that log will have a log of your cookies. Yes? Are cookies the only thing? No, it's just the easiest one to explain. JavaScript can do a lot of stuff. Like, it can register event handlers that get called every time a key is pressed on that web page. So it could put some event handlers that wait for you to log in on the password page and like record the password you typed in, or do other stuff. Basically, anything that you can do on a web page, JavaScript on that page can do too. Okay, so what this would look like is there's an attacker who's trying to harm the victim, and there's this web server that's not malicious, but it's just kind of a patsy here. It's not sufficiently careful, has this bug in it, basically, this XSS bug, that enables the attacker to kind of manipulate it into causing harm to the victim. So what the attacker does is injects malicious script into a page on forum.com. That's like me updating my status message on Facebook to put the script tags on my Facebook page. And then somehow get the victim to request that page. This is maybe the phishing parts. Maybe the attacker sends an email to the victim and says, here's this awesome page I just saw, you got to check it out. Or, oh no, your account's about to be canceled. Click here to like, renew it for another year, or whatever will get the victim to click on links. Usually it's not that hard to get people to click on links if you scare them enough. So the next step of the attack was somehow the attacker gets the victim to click on this link to request that page that contains the malicious JavaScript. The victim browser does so. The web server returns the page, which now contains malicious JavaScript. The victim's browser runs that malicious JavaScript, and that malicious JavaScript can do harm. Like, for instance, extract session cookies or other valuable data and send it, exfiltrate it to the attacker, to the attacker's website. Okay. So this is like me getting Emma to pass a note to the Hulk, who tells the victim to do something, and the victim does it. That's stored XSS, and the relevant bit about stored XSS is the attacker does this once, and then all users who visit that page now will be attacked. Oh yeah, another thing that this malicious JavaScript could do is when it runs, it could start making requests to the forum or to Facebook. Any actions that the user could take, the JavaScript could take on their behalf, like change the victim's profile from private to public, or start posting embarrassing status messages on the victim's page, or add me as start following me and giving me lots of thumbs ups or whatever. Okay. Reflected XSS is a little different. It's just a little bit harder to understand. But in reflected XSS, the attacker can get some malicious script into a page, but it's temporary. It's not persistent. It like only appears in responses to this malicious URL. So the example I was showing you before with the code, the vulnerable code, was a reflected XSS. If I sent a URL with the name Dave, Dave would only appear back to me. It wouldn't, other people who visited some other URL wouldn't see Dave. And a classic example of this would be an early version of like Google search, where when you type into your browser a search term, your browser makes a request to google.com search question mark, and then puts a parameter where the value is the search term you entered. So if you search for Evanbot, your browser loads a URL like that. And google.com responds with an HTML page that has a listing of the search results. But in Google, at the top, will say, you searched for Evanbot. Here's 10,000 results for the search term Evanbot. And so the search term is echoed into the HTML response from google.com. Now, Google's very careful, but if they were not careful, then one could construct a URL that puts JavaScript into the search term. And that JavaScript would be copied into the HTML response from google.com. And any browser that visited that URL would display a web page that contains this JavaScript, would run the JavaScript, and the browser thinks that JavaScript came from google.com, so it'll let that JavaScript do stuff with your google.com account, like access the session cookies that your browser has for google.com, or like load Gmail and send emails or something like that. So if I can somehow get you to visit that malicious URL, your browser will run the malicious JavaScript, and that malicious JavaScript can access your Google account. But it only affects you if you load that URL. It doesn't affect anyone else. This is called reflected XSS. And in a reflected XSS attack, the attacker creates this malicious link that contains some malicious parameter, sends it to the URL and sends it to the victim, and gets the victim to somehow load that URL or click on that link. When the victim clicks on that link, their browser requests that URL from, let's say, bank.com, in this case, instead of google.com. And that URL has been chosen by the attacker, so it was chosen to include some malicious JavaScript tags inside the URL parameters. And the bank, if it's not careful, will respond with an HTML page that now contains the JavaScript tags and the malicious JavaScript that the attacker provided. And then the victim's browser will see an HTML response from the bank. Aha, the bank wants me to run some JavaScript. I'll do that. And I'll let that JavaScript have access. The victim's browser will let that JavaScript have access to all content related to bank.com, including the browser's session cookies for bank.com, stuff like that. So when the victim's browser receives this response from bank.com, it executes the malicious JavaScript, and then that malicious JavaScript could do things like read the session cookie, the session token for bank.com, and send it to davewagner.com. And now Dave Wagner is able to log in to the bank, but as the victim. Or could send requests to the bank, and the bank will think that that came from the victim. It did. It came from the victim's browser. It'll have like the cookies attached and everything. So that JavaScript could cause the victim's browser to like go to a page that like transfers money, and then like click OK on that page and click confirm and click yes, I really do want to, and a money transfer will now happen. Well, banks try to have a secondary level of defense where they like might send your text message or whatever, so they might actually stop this. But most websites don't have any way to stop this, because there's no way the server can tell the difference between browser sending a request because the user wanted them to versus browser sending the request because the attacker is exploiting an XSS vulnerability. Those requests look exactly identical from the perspective of what the bank can see. Okay, so that's a reflected XSS. Part of reflected XSS is the attacker has to force the victim to load a URL chosen by the attacker. How do attackers do that? There's lots of ways. We talked about one, send a phishing message. hey, your account is about to be canceled. Click here to renew. That link actually is the malicious URL. Another way is to lure the victim into visiting the attacker's website. Harmlesscatpictures.com. This is totally safe, really, I pinky promise. And then on harmlesscatpictures.com, there's some HTML that like loads an image that is at that URL. And so when the victim's web browser goes to load that web page, it'll make a request for that URL provided by harmlesscatpictures.com. In other words, provided by the attacker. Another way is to buy ads. Get your free TV here. Click now to be the first 100 people to click get a free TV. But the link for the ad actually goes to this malicious URL. Lots of ways. They all involve kind of like con or social engineer someone somehow. No, not 100% successful, but often are successful. So there's a lot of moving parts here, and this is pretty confusing stuff. One thing that many people find particularly confusing is cross-site scripting versus cross-site request forgery. Oh my gosh, it's so hard to keep straight. They have similar names. They both have cross-site in the name. And they also have some pieces that are similar. They both involve getting the victim's browser to visit a malicious URL. The attacker somehow gets the victim's browser to visit this harmful URL. But they're not the same. They're different. The way you can tell the difference, one way to tell the difference is that XSS involves malicious JavaScript. Cross-site scripting involves script. CSRF doesn't need to involve any script. So if it's about what is the malicious URL or the malicious link, if the malicious link, just sending that to the website is enough to cause harm, is enough to cause like money to be transferred, CSRF attack. If the malicious link doesn't immediately cause harm, but it like causes malicious JavaScript to be sent to the victim's browser, which then causes harm, cross-site scripting. So CSRF is more immediate harm. XSS is like kind of an extra step involved. You send something to get the website to send JavaScript to cause the victim's browser to do some additional thing. These are different. So defending against CSRF is not enough to defend against XSS. Question?
The examples so far, like there's just one website, right? Like Google.com or like Bank.com.
Just one website. Yeah, implicitly there's two websites. There's like attacker.com and there's like bank.com, or attacker.com and facebook.com. I've been playing the role of an attacker. I didn't say it, but usually the way this shows up is I have a website, attacker.com, or harmless cat pictures, really harmless, I promise, that is doing the attack actions, tricking, causing people's browser to visit this malicious URL. It's not fundamental. It's true. It's true. Yeah. It could happen without the attacker having any website at all, just like an email or something like that. But it's a common way they happen. Attacker sets up this malicious website, gets people to visit it, and then this malicious website is like getting visitors' browsers to visit the malicious link. Yeah. Did you have a question? Other questions? Then now we desperately need a break. So we're going to take a short break, just like a 2-minute break. We'll get started again real soon. 2-minute break. Okay, break over. This is just brutal, but we're on a march. We're on a march through this. So I wanted to show you an example of an XSS vulnerability in the wild, and what better place than to show you than on Berkeley's own systems, because everybody makes this mistake. So rather than making fun of someone else, let's make fun of ourselves. CalNet authentication page. We've all hit anytime you want to log into your Berkeley account. 4 years ago, EEC student noticed that that login page has an XSS vulnerability. And we've been teaching about XSS for, more than a decade. So this is, this is not some new thing. And the way the login page works when you log into CalNet is there's a form, you type in your username, you type your password, they get submitted when you click submit, they get sent in a request to the server. And there's also a third piece of data that gets sent to the server in that request. That's some other stuff that's used by this application to keep track of, like, for example, once you log in, which website should it direct you to? Should it direct you to Bmail or to BCal or YouTube or whatever? Okay. This student was playing around with just reverse engineering how this works and playing around with it, sending requests, strange requests with strange values for these fields. And notice that if you change this third field to have some other value, just just overwrite with some random garbage, then the server notices, whoa, that's not the format I was expecting, and throws an error page, sends the browser an HTML document that contains an error message. And that error message shows something like what's shown here. Error, this is a bad request, something wasn't right about it. Maybe you want to let our system developers know because it's a bug, or maybe just something weird is happening. And in case you want to contact developers, here's some debugging information that might help them. And in the error message, it included a copy of the data, the malformed data that was in this third parameter. Just copies it in there. Okay? Copies it byte for byte. So something in a URL parameter gets copied byte for byte into an HTML document, into a response from the server. That's a classic XSS vulnerability. Because if we construct a URL where that third parameter contains a value that is stuff that has a script tag and some JavaScript code, then the server will respond with an error page that copies this into the error page, and then the browser will interpret that as JavaScript code and run it. Okay. So one could at the time construct a URL that, if you load it in your web browser, would run this JavaScript and pop up a message in your browser. And what this JavaScript could do, instead of popping up a message in your browser, it could do other stuff in your browser. Like if you were currently logged in to CalNet, it could take your session cookies for CalNet and exfiltrate them. Or it could overwrite, JavaScript can overwrite the current page with some other HTML, overwrite the current web page with some other HTML that looks like a valid login form with a username and a password, but the submit button doesn't go back to CalNet. It goes to hahagotyoevil.com, to the attacker's website. And then you might briefly see this error page flash up and be immediately replaced with a login page. You'd be like, the login didn't work. Let me type my username and password again. And you've just given your username and password to the attacker. Okay, so XSS vulnerability in this like super critical code that you would figure is like, if there's one thing that's got to be secure in all our web systems, it's the login authentication system. Man, we're probably looking at that super carefully. And we were, but it's just too easy to make this kind of mistake. We're human. We make mistakes. That's what we do. And as a result, like anyone could like steal other people's Calnet accounts. And how did this happen? How did this bug manage to make its way into the code? Well, the Calnet page is like based on some open source software that had a sample page that had this XSS vulnerability in it long ago, and we copied from that sample page and customized it for Berkeley. And then the people who made that open source package like discovered the bug and realized like, this is no good, and they fixed it. They modified their sample page to be fixed. But when you update the software package, those updates don't propagate into the custom version that we created based on that old thing. And so we still were basing our login page off of this old buggy sample. And so we were still vulnerable, and that fix didn't help us. So we ended up with vulnerable code. Oops, easy mistake that anyone could have made. So how do we defend against cross-site scripting? There's a bunch of standard defenses. There's many ways you could do it. But basically what we do is we do some kind of a sanitization. The problem is this blind copying of whatever is in the URL parameter into the output. Don't do that. Don't copy blindly. Only copy stuff that's safe, and don't copy stuff that's unsafe. And there's certain characters that are special in HTML. They like indicate markup rather than content. They indicate like tags. So what we're going to do is those special characters, those characters that an HTML parser will treat as special, we're going to treat as unsafe. And we're going to make sure that they cannot appear in that value, or they're removed if they do appear, or they're replaced with something safe if they do appear before the data is inserted into the HTML page. That's how we'll make things safe. And probably maybe one simple way to do it is to just remove those characters. If there's any less than sign or greater than sign, remove that. Copy the rest into the HTML response. That's okay, except it might be a little annoying. It's safe, but it might be a little annoying if I make a forum post or make an ed post about how, because x is less than y, therefore x squared is less than y squared, or something like that. And then whoops, all the less than signs got removed because they were special characters and it's not safe to include them. And now my ed post doesn't make any sense. So instead, what we usually do, a better defense, is don't just remove those characters. We replace them with characters that will display visually the same way, but they will not be interpreted by the browser as a markup, as tags. And HTML defines a way to do that. Because less than starts a tag, you need some way to show an actual less than that's not a tag. And the way HTML says to do that is do this crazy like escape code thing. And so if you do this replacement, if the web server does this replacement before including text into a HTML response, then it'll be safe. Then no tags, no script tags or any other kind of tags will be able to be inserted into the HTML. Only like text content will make its way in. Okay, and it's a little tricky to figure out exactly which characters are safe and exactly what to replace them with, so you should use a library, otherwise you'll guarantee to get it wrong. Okay, so instead of putting name in there, we call a function, this library function, escape string, which just modifies it by replacing less thans with ampersand, LT, semicolon, and so on to make it safe. And so then if an attacker causes your browser to visit this URL that has some script tags in the parameter, before it gets copied, the less than signs get replaced by this code. And so what's actually in the HTML sent to your browser is not anything that'll be interpreted by your browser as a script tag. It'll show up as funny looking code like output, but no JavaScript will run. So this is the accepted defense against XSS. The tricky bit, of course, is that you have to remember to call HTML.escapeString on all the like dynamic or untrusted content. If you forget that, if you just put name in there, it'll look like the web page looks good with normal testing, with normal values, but it'll be silently insecure. So this is kind of like a dangerous kind of a defense, because if I don't do anything, the default is insecure, and I have to do an extra step to make it safe. And people are not very good at remembering to always do the extra step. It's why the game Simon Says is fun. It's why we like lose at Simon Says, because sometimes we forget about that. Yeah. Why isn't this built into HTML by default? I guess we'd have to think how it could be built into HTML by default. And I think this is a consequence of the fact that the interface between a web server and a web browser is a string that contains like this HTML markup that's interpreted in like this syntax. As long as that is the interface that's defined on the web, you're going to be vulnerable. How could we have designed the web so it's not vulnerable? I guess if what websites sent you was a parse tree, a tree data structure, where each node represents like a tag, like bold, or start a new paragraph, or everything under here is JavaScript. And then the content is in the leaves of that tree. Then I think you might be safe by default, because the natural way for a server to add some dynamic content into the page would be to add a new leaf with that string, not to like start adding new nodes that are tags. And so you'd probably be safe by default. So the root of all evil here is strings in some sense. And the way to be safe would be to use data structures instead of strings, or represent a data structure. Why was the web designed with strings instead of data structures? I think strings were really convenient. Like a string is like really simple. You can like print it out. You don't have to define a special data structure or how to encode that. You could write a 3-line script that generates HTML. I can write a text file that has the HTML. I don't have to write in some crazy binary format. It could have gone some other way. Maybe the root cause is because when the web was designed, nobody had anticipated this type of vulnerability. I'm not really sure why. If we were to design the web today, we might do it differently. But the thing about the web is like it was initially designed by physicists to share their papers with each other. So it was like people who trusted each other. And then eventually started showing cat pictures and so on. And you know, wasn't when it was designed, nobody was really thinking about like, oh boy, we gotta anticipate all the security problems. And I'm not sure whether anyone would have anticipated this particular problem until they built it and had experience with it. But now it's hard to change to a new design, because if I'm a web server and I want to start serving my web content in some other way, no browser will understand it, so there's no point. And if I'm a web browser and I want to start accepting content in some other way, no current website sends content that way, so what's the point? Why would I spend $10 million to add that feature to my web browser, or $10 million to add that feature to my web server? So we're kind of, historians call this path dependence, where you can kind of get, there's like a valley here and a valley here and this tall mountain. And like I could take the left fork, I could take the right fork, but once I'm deep down in this valley, it's really hard to get over the other valley. I have to climb up really high, come back down again. And so those early decisions are just, we're kind of semi-stuck with them now. All right, so escaping is defense against XSS, but the problem is the program has to remember to escape every place where they include dynamic content in the page. So not ideal, and fortunately, developers have come up with a better solution that doesn't require you to do something or else you're vulnerable. And today, the accepted way to do this is don't build up HTML responses with string concatenation. Use templating systems. And in templating system, the website developer writes what looks like an HTML, but it can have these like holes in it. These curly brackets indicate a place where value will be filled in later. And the templating system is a software library that knows how to fill in values and do so in a way that's securely and will not be vulnerable to XSS. And the way it does that is automatically does escaping of those values when they're filled in. And because it automatically escapes, programmers, the website developers don't have to remember to do that every point. And so it's not so error prone. So use templates with automatic escaping. Another defense is called content security policy, which is supported by many web browsers. It's an optional feature. It allows the website to specify to some limitation on what kind of JavaScript can appear in this page. Like, for instance, no JavaScript tags are allowed in this page. If you see any, don't just ignore them. Website can tell the browser that, and the browser will follow that. The website can say, JavaScript will only appear in external documents and only documents on the following domain. Don't load any other JavaScript. That allows the web server to make sure that the only JavaScript that's loaded is JavaScript that is trusted. Basically a whitelist of trusted JavaScript. And that way the attacker cannot introduce any malicious JavaScript in, even if there is an XSS bug in the code, because the browser will refuse to execute that JavaScript, the other JavaScript. Okay, so this is another good solid defense. And the only shortcoming is there's some old browsers, especially mobile browsers, that some percentage of the world, I looked it up before lecture, and it's like 4% of the world's running old ancient browsers that haven't yet implemented support for this. And like people, it's probably old Android or old something phones that are not getting updates anymore. And so they're not going to be updated until someone just gets rid of that device. So unfortunately, you can't yet fully rely on this as 100% defense, because some people will visit your website from browsers that don't support CSP. That's cross-site scripting. Woo! Oh man, I have more I wanted to show you. I have so much more today. I'm like going way slower than I wanted to. Okay, but let's take a break and see how you're doing with XSS. Do you have questions about XSS before I move on? Yeah. Usually CSRF vulnerabilities don't involve any XSS. And XSS vulnerabilities typically don't imply any CSRF. Yeah. Yeah. If I sent you an email and you clicked on that link and that your browser sent a request to Twitter that caused you to follow a bunch of people, CSRF. If I sent you an email and you clicked on that link and you send something to Twitter that caused Twitter to send you back some JavaScript, and the JavaScript then caused you to follow a bunch of links, XSS. Often websites will have defense against CSRF. So just sending a request is not enough to follow some people. It'll like require an extra confirmation or something crazy like that. If I can do an XSS attack, the XSS can do anything that you can do. So the JavaScript can do anything you can do. So it can do all the confirmation needed. So even if the web server is vulnerable against, even if Twitter is secure against CSRF, has defenses against CSRF, if they have an XSS attack, I might still be able to get your account to start following lots of people. by sending the request to follow and then sending the confirm and all of that. And JavaScript can like send multiple requests and script all that up. Control the browser, basically. So JavaScript basically controls the browser, everything associated with that one website, that one domain. Yeah.
That won't be dangerous because it'll be sandbox that site.
Yes.
That site will be
Yes.
relevant to only that site. And
Yep.
request.
Yep.
Like the danger is when somehow get that reflected or get that stored in a trusted website.
Yes, exactly. Any website, some untrusted website, can have malicious JavaScript on it, and the browser, same origin policy, will make sure that malicious JavaScript can only hurt that one website, can only access stuff from that one website. But the danger is if an XSS vulnerability on a trusted website can be used to like get that malicious JavaScript injected into the trusted website, then now like that JavaScript can do stuff with the trusted website's content. Anything on that trusted website's content, yeah. And that breaks the isolation. And that's, the isolation is the main security thing the browsers are trying to give you to make it safe. They make it safe to browse multiple websites and browse anything, even ones you don't trust and so on. Okay, I also want to tell you about UI attacks, which are kind of cool. They're kind of fun. Total change of topic, has nothing to do with XSS, completely unrelated, not a code vulnerability in a web server at all. It's like something fundamental to how browsers work. And UI attacks involve tricking the victim creating this fake world where the victim thinks they're doing one thing that's harmless, but actually the effect or what the browser does is something really harmful, and the victim doesn't realize that it's being interpreted that way. And there's clickjacking and phishing. And I want to start by telling you about clickjacking, which is like mind-blowing. It's like, oh my gosh, so clever, such a clever attack. The idea is a web browser trusts, anytime there's a click on a web page, the web browser like trusts that and trusts that that came from the user, like only a person could cause this mouse click. And so therefore the user must have intended that. And so the browser like is the agent of the user and will do whatever the user wants. So therefore it must be a good thing to do what that click said to do. So if malicious website can somehow cause a click to happen that's bad, that the actual human would never have wanted to happen, the browser will start doing bad stuff, thinking the human wanted, but the human didn't. How can it do that? I'm going to show you how. It can't. I basically can't. One website, they're isolated. So one website cannot like simulate a click. Evil.com cannot simulate a click on bank.com. It can't. You as a human can click on bank.com. So the idea is going to be to get you to make a click on bank.com, but you don't realize you're clicking on bank.com. You think you're clicking on catpictures.com. You think that click is a totally harmless thing. That's what you think. That's your view of the world, how the way it looks to you. But from the browser's interpretation, you, the human, were clicking on bank.com to transfer the transfer money. You, the human, must have wanted that. Let's still do the transfer the money. So we're going to mess with what's shown on the screen to change like the way that you interpret that differs from the way the browser is going to interpret it. Here's a dumb example of this that I'm sure we've all run into. You go to this web page. I search for some software I want to find. I get to this web page. It gives me the software. And which button should I click to get the software? Well, there's some ads on there that are also showing download buttons. They're trying to get you to click them instead of, I think it was intended to be that green one on the left, not the other green one on the top or the red one on the right. But if you're not a very sophisticated user, you might see download and click. Okay, very simple kind of a spoofing thing. The user thinks they're clicking download on this website. They don't realize that it's actually like parts of the image displayed here are actually not from this website, download.com. They're from some other party, the advertiser. And so we continue to see this attack today. But here's a little, let me show you something that's a little more sophisticated. Let's say you go to berkeley.edu and it has a link to go to their like fundraising site. And let's say berkeley.edu really wants you to go to that fundraising site. This is a crazy example. It's not a very realistic example. I don't know why that would be so important to get you to click on that fundraising site. So don't take this too seriously. Okay. But you don't want to go to the fundraising site. You're like, whatever. I'm paying tuition. What do you mean donate? Here's what a malicious website could do to cause your browser to go to the fundraising site as though you had clicked on it. They could load this iframe, which allows to load a web page inside a web page. So this malicious web page has some content, and it also loads berkeley.edu inside it in an iframe. So there's the malicious web page. At the top, it has some text, and then inside it is a rendering of berkeley.edu. Okay. Now you're still not going to click on that. You don't want to like donate. And the malicious website's JavaScript can't click on stuff inside the iframe because it's a different origin, different domain name. So that browser won't let it do that. That would be breaking isolation. But what the browser will let the website do is put some additional content. Like underneath, I guess I said. I don't know why that was important. Well, you won't see it because it's underneath. On top is berkeley.edu. Underneath is the enticing content. But on top is showing and the underneath isn't visible because the on top is on top of it. So let's tweak this. Let's change on top to be semi-transparent. That is a thing one can do in HTML, is load an iframe, but it's semi-transparent. And underneath it is that you want to click on this, just barely visible. Well, still. But let's make it even more transparent. In fact, let's make it all the way transparent. Now what the user sees is you want to click on this. Well, that's a silly example. Maybe it's not you want to click on this. Maybe it's click here, the first 100 people to click here get a free TV. Great, I could use a free TV. Click. From my perspective, I think I'm clicking to get a free TV. What does the web browser think? Yeah? Clicking on the iframe, which is on top, even though it's transparent, it's on top. So clicking on the berkeley.edu website on that link to the fundraising. So from the browser's point of view, I asked it to visit the fundraising site. From my point of view, I wanted the free TV. From the browser's point of view, I wanted the fundraising site. And so the browser goes to the fundraising site, even though that's not what I wanted. So this is stealing the destination of clicks. I thought that I'm clicking on one thing, but actually the effect is as though I was clicking on another thing without me realizing it. And this is a way that a malicious website can get clicks to happen on some other web page. It could be that this malicious website is instead some really cool game that I click around like crazy to play the game and I love it. It's awesome, Candy Crush for free or whatever. And the transparent thing on top is like PayPal, and it's like authorizing, payment transfers, emptying out my account to the attacker. And I don't realize that I'm actually approving all these transfers on PayPal. Yeah. Yeah.
We know that when we're clicking, if we can click on white space, because if we're clicking on white space, there's probably, and usually we should only be clicking on buttons and stuff.
Yeah. So this malicious website is going to load a Candy Crush game that it knows right where it's going to get you to click. Click here to like, win the game, whatever. You're going to click there. It can totally predict where you're going to click. And then it arranges for that location to be where the PayPal confirm button is.
No, but
So you're probably going to have no idea that there's any shenanigans going on here.
I'll show up on the left page, like the crowdfund effort.
Wherever it is, let's say the PayPal page is like, do you want to approve transferring $100 to this destination? Click confirm here. Let's say it lands the confirm buttons right here. Could be anywhere. The malicious web page shows the Candy Crush thing where there's like, about to be 5 in a row. If I just click right there, I got 5 in a row and like they evaporate. So I'm going to click right there. And I think I'm evaporating 5 in a row, but I'm actually confirming PayPal. This thing? Yeah, my browser doesn't show that anymore. Used to be they would, and like no one looks at that. Come on, I'm not like, I'm a security person, and I'm not like, oh boy, before every time I click, what if I'm being attacked? I better check. Like, come on, who's got time for that? So in practice, this works super, super effectively. You could imagine it would be possible to be like super paranoid and like avoid getting caught by this, but like, let's get real, no one is. Yeah. How do we defend against this? Before we design defenses, yes, it's so hard. Before we design defenses, I want to show you that like just more variations of this attack so you can like get the feeling of how hard it is to design a defense. I mean, if you want to throw one out there, you can. Some little pop-up. Something showing where you're actually clicking. Yeah, I think from a user, yes, but except that from a human factors point of view, what we've discovered in studies is that we're security people, but users are not security people. They don't start from the attitude of, I might be under attack all the time. I better be constantly vigilant. If I see something weird, it's probably an attack. I better check and make sure I understand everything that's going on. No, most users don't understand what's happening on this web thing. That my kid is like tugging on my arm right now and saying, I'm hungry, can you make me dinner? And like, I just want to, order takeout or whatever. So unfortunately, those kinds of defenses just don't seem to be very effective, even though they seem like they could be, or maybe they should be. All right, so here in this attack, the legitimate site is like invisible and over the enticing content. You can also do it the other way around. You can have the enticing content on top. No. What am I saying? Yeah, like Pal was on top here, but invisible. Why? I managed to confuse myself somehow. Oh, yeah, okay. I mean, you could also have like some malicious site that I want is trying to get clicks on, like download this malware, put that on top, but make it invisible. The user clicks on the legitimate site, think they're clicking on the legitimate site, but the click actually is stolen by the invisible on top. Also, it turns out it's possible to have a legitimate site that's visible and then put malicious site over top of it that shows different content. So how much, if you click on pay, how much are you approving PayPal to transfer to AdBlock Plus developers? 15 cents. No, except yes, except no. No, yes, because yes, except no, because this is actually, the PayPal is actually an iframe, and over that is a malicious site that is showing content. But this is actually showing on the PayPal site is okay to transfer $1,000. But the malicious site has put over top of that content showing 15 cents that's covering up just the part with the payment amount is. So you just approved $1,000, even though when what you could see, it looked like you were approving 15 cents. You were okay with 15 cents, but you weren't okay with $1,000. Another nasty attack is temporal attacks. JavaScript can detect where the cursor currently is, predict when you're about to click on something, and just before you do, change out what website is like being displayed. So you're playing Candy Crush. It's the Candy Crush website is the only thing displayed. It can predict you're about to click right here. And just before you do, a millisecond or 100 milliseconds before you do, replaces out the Candy Crush website, instead shows the PayPal website and arranges it so the confirm button is right where you're about to click. You click, that goes to the PayPal confirm, and then they change it back to Candy Crush 100 milliseconds later. Maybe you'll notice some funny flash, maybe you won't even notice. Crazy, crazy. So what, at the time you formed the intention to click, what was displaying was Candy Crush. But at the time the click happened, what was actually there was PayPal or some site where the attacker wants to redirect your click.
Outside, it fails if you're, even if.
Yeah. You know, it's like we're gonna play Dance Dance Revolution online for free. A rhythm game where the goal is a user, your job is to copy the rhythm exactly. Now, your actions, if you're trained well, are very predictable, right? Gives you an easy one. You're like, yeah, I got it 100%. Yeah, I'm the best. Yeah, go me. And what you don't know is that one of those clicks actually went to PayPal. Okay. Here's another attack. Like, it's just crazy how many of these there are. One of the things that a website can do is change the style of the cursor, provide a different image to use as the cursor, so that instead of having a hand, if I want, I can have a cute mouse picture. A cute, like, little picture of or a cat, that's even cuter. A cute picture of a cat, and the click happens under the cat. Here's the wild thing a website can do. Can change the image of the cursor so it's a hand, the same hand, but not in the same location. You got some white area and then a hand offset. So the click is going to happen at the center of this image, but the hand is off on the side. So it looks to me like I think I'm clicking right here where the hand is, but the browser's interpretation of the click is offset. And by specifying a malicious image, which any website can do, it causes an offset between where I think I'm clicking and where the browser thinks I'm clicking. And then can arrange to have, malicious content over here, this thing that the malicious website wants me to click on, the PayPal confirm or the downloaded malware or whatever. And then, some good stuff, click here for the free TV with a, at that known offset. And I move the cursor around and I arrange so that the hand is right over, give me the free TV, but the actual center of the image is over the download malware. Ah! So how do we defend against this? Oh, it's really hard. There's so many ways to fool users. And one of the ways is to require that browsers do today is they require that like really critical, high criticality actions, the confirm box, like completely separate from all other content. Like confirm boxes for your browser, like freeze and like darken all the other content and then like put a confirm box and the confirm box is always on top and like arranges that clicks can only go to that, not to anything underneath. Firefox actually has it go the confirm things go partly covering up the address bar and partly covering because web content can't partly cover the address bar. The idea is that you'll be able to tell that this can't be faked. I think no user's ever going to notice. I think that's kind of a pointless measure. And then in addition, to ensure this changing out stuff over time, they put a delay. So before you can click OK, you have to wait a second. And this is showing, has to be showing for a second before you can click OK, and then you can click OK. And that's trying to defend against this, change things out for 100 milliseconds. If it gets changed out and then 100 milliseconds before you click, this gets shown up, the click won't have any effect. This has to be showing for at least 1 second for the click to have effect, so the user will hopefully have noticed and it'll have affected their intention to click. So these are the kinds of defenses that people put in place. Like require confirmation from users on significant actions, force that confirmation thing to go through a separate system where it gains control of the screen and and receives clicks. Force confirmation by some separate thing that's not through the browser, like an SMS text message. Various hacks that websites can use to say, I refuse to be displayed within an iframe. All sorts of defenses. It's challenging. The other UI attack is phishing. And this is one that hopefully you're all familiar with. Some attacker sends you an email that says, oh my gosh, we're going to close your account. But if you still, because it hasn't been active, but if you still want to use it, no problem, just click here and log in and we'll re-enable it for another year. And if you believe that that's coming from the real PayPal, you might say, oh yeah, I want to keep my account, I'll click there. So you click there. When you click there, it goes to a website and you see the PayPal login. So you enter in your PayPal email address and password and click login. And it behaves just like you'd expect. And it says, oh, by the way, could you confirm a few things just to make sure that we've got your latest contact info, like your phone number and so on. So you're like, okay, yeah, well, I guess. You start typing that in and you click continue. And then it's like, hey, we need to confirm a few more things. Let's just make sure we have the right credit card number for you. Could you type your credit card number in again? This is just a security measure, nothing to worry about. And so if you're very credulous, maybe you start typing in your credit card number and your social security number and like everything. Why would a user type all this stuff in? Because they believe they're talking to PayPal. But actually, unbeknownst to them, that link doesn't go to PayPal. That link goes to evil-attacker377924.com. And they have crafted the look and feel of their web page to look exactly like PayPal in all visual respects. It's just that it's not actually PayPal. So the data is not actually being sent to PayPal. The password and credit card number are being sent to the attacker. Surprisingly, it's a very low-tech attack. It's very easy to mount. And even if it only works against 10% of people or 1% of people, it's easy to automate. Send to 1 million people. Maybe you're successful 0.1% of the time. Woohoo, we're in. Okay, so this is a phishing attack. And it works because it's kind of hard as a user to defend yourself. You got to be looking at the address bar, and on a mobile browser, the address bar may even be showing, and it could even be hard to notice this. You got to be super vigilant. One moment of inattention and you get fooled. So it's exploiting aspects of human psychology. Yeah? Yeah. The phishing stuff doesn't require any JavaScript. Oh, for the UI stuff. Could there be hoverjacking? Yeah. User hovers over something and it does something. That's cool. Maybe there's an attack there. Maybe you can invent a new attack. Get your TED Talk ready. I don't think that most websites treat hover as any significant, will take any significant action just from hovering. So I can't think of any examples where an attacker could cause something seriously harmful to happen by basically creating a hover or simulating a hover. But maybe there is something. Maybe you'll think of something. Yeah. I mean, it feels like these kind of UI attacks are kind of endless, and these are just examples, but there's probably lots more. Yeah.
I'm not sure if it's for every website, but it usually shows what URL you're gonna go to by clicking on something.
Uh-huh. Yeah. But beware, that's not actually reliable. I don't know if you know this, but it will show you what, it might show you what URL is that you're about to go to, except just before you click, it can change. Because JavaScript can run asynchronously and change the actual link. And so it's displaying that you're going to go to good.com. And if they can predict when you're going to click 100 milliseconds before you click, JavaScript changes the link out to go to evil.com. So it's not as useful as you might think. And then also, most users are not really paying attention to that anyway, so it's not as useful as you might think for average users. Like, oh, it's so hard. It's so hard to stop these attacks. There's so much complexity. Okay. So back to phishing. How do we stop phishing? Well, one way is to tell everybody, don't click on any links in your email. What do you think of that defense? What? People will forget. Yeah? There's good links in my email. That's stupid. Like, come on. I click on links. It's like, I get links in the email all the time that I need to click on. You know, I get like share invites to Google Docs. And I mean, this is why I use my web browser to like click on stuff. It's crazy. It's crazy advice. So I see this advice all the time. It's like, drives me crazy. It's like, we built this system that was insecure. It's not safe for use by humans. And then we blame the humans by saying, don't do that thing that the whole system was designed to enable you to do. Like, okay, I hate that. Yeah, sorry, got worked up a little bit there. Okay, so that's one defense, not a very effective or reasonable defense. Another defense is that people have tried is to say, aha, the address bar, the browser address bar is your defense. The browser address bar is shown by the browser. Users teach users to check what's in the address bar before entering their password. If it says paypal.com, you're good. If it doesn't, you're not. Make sure that what's in the address bar matches the site you think you're on. Kind of nobody really suggests it anymore. Any idea why not? Hard. Hard, yeah. Anything else? It sucks. It sucks. Why that advice sucks? Why does that advice suck? Yeah? The user might not know what's the correct URL. Is it like paypal.com or paypallogin.com? Is it like primevideo.com or amazon.com or amazonprimevideo.com?
Does JavaScript change the URL to?
No, fortunately it can't. The address bar is one thing that is safe from JavaScript messing with. Any other reasons it sucks? Yeah? Could be an XSS against the site. Though usually phishing is not really about exploiting vulnerabilities. It's low tech. It's super low tech. It's like just doing the dumb thing. Yeah? Yeah, the attacker could like buy a domain that looks similar to the real one. And what can you give me an example of how they could look similar to PayPal.com? PayPal, but instead of the L, there's an I. Users might not notice. Yeah. Yeah. And then, so users have to be super vigilant. It's like 1 pixel difference. And then on top of this, the whole human factors perspective is crazy. It's telling users, before you do anything, you have to remember to do this extra step. That's an unreasonable burden. What if someone forgets once? It's hard to, it's not part of my normal workflow. It's not reasonable. It's not reasonable to expect people to do that. People are not going to do that. They're not going to check. So it's kind of like asking users to like make up for the deficiency of the system. So that's not a very good defense. Also, there's spoofing possible. There's crazy ways to spoof the address bar too that like blow me away. Like stuff like that's a domain name. It looks like a URL because it's got a domain and slashes, but no, these aren't slashes. These are a crazy Unicode character that's a diagonal thing that can appear in a domain name and it's not a slash. If you are not like uber technical expert, there is no way you're knowing that that is an unsafe domain as opposed to actually pnc.com. What about if we ask that it should be HTTPS? No, the attacker can set up an HTTPS website. What about if you check the URL? Well, like you said, the URL you can put in, like make a near match. In fact, that looks like apple.com, but actually there is Russian Cyrillic alphabet letters that look very close to an APPLE, but they're not actually actually the A, the P, the L, and the E. They just looked very, very, very similar, maybe identical. So it's actually a different domain. If the attacker registers that domain, they can steal passwords. Another thing is there's often multiple characters that have a very similar visual look. Those are called homographs, and you can replace characters in the domain name with the homograph, and no user is ever going to be able to tell the difference. And like, oh, so many things that make it hard for users, even if they're super vigilant, to detect attacks. And even if we somehow stop all of those, here's yet another attack. That's surely Bank of the West, right? It's got everything. It's got HTTPS. It's got the right domain name, but no. It's actually an image rendered inside attacker.com. There is no browser window with Bank of the West. That's a simulated browser window being simulated by attacker.com, JavaScript on attacker.com. It's displaying pixels that look like a browser window and that like respond like a browser window. And so really hard for users to protect themselves by checking the address bar and checking that they're on the site that they think they are. And users aren't security experts. Like I drive a car, but I'm not an expert in how a 4-stroke engine works. And most users are not experts in how browser security works. Attacks are uncommon. Usually users normally don't expect malice, and so they're not really primed to be prepared for malicious action. They're just sort of doing what they always do. So we shouldn't blame people. We should devise systems that are more resilient. And one attempt to do that is to use two-factor authentication. So when you log in, you get a little buzz on your Duo app, or you get a text message with a code, and then you've got to approve the login in your app or enter the code in on the website. So what does that do? That means that even if I get fooled into going to the wrong website, I think it's PayPal, but it's not actually PayPal, and type in my PayPal username and password there, the attacker has got my PayPal username and password, but that's not enough to get into my account. They also need this app, and they don't have my phone, so they can't do that. Or they don't have a way to receive text messages, and so they can't log into the account. That password is not enough. So two-factor authentication basically is today the way that we try to defend against phishing. It's too hard to reliably prevent people from getting scammed into revealing any secret they know. So authentication should not rely just on a secret that people know. It should also rely on something else can't be phished, like a device, something they have.
I'm gonna ask for two-factor authentication. I'm gonna say like, I could ask for like some code. How hard would it be like just to brute force that code? Because I know that was
Usually the codes are long enough that you're not going to brute force it. Like it's a 4 or 6 digit pin or something like that, and they'll like let you make 3 wrong attempts and then lock your account or something. So you're not going to brute force it. It turns out, and I'm not going to say any more because I'm out of time, not all two-factor authentication is the same. Clicking approve on the Duo mobile app turns out to be much safer than receiving a 4-digit code by text message or a 6-digit code by text message and type it into the website. And if you're bored and you're standing online at the post office or in the shower or whatever, and you could think about why that is. Why is it not much less safe to be texted a code? In fact, Berkeley is trying to disable all two-factor auth with text to code and force you to use the app because it's so unsafe. So you don't have to figure that out now, but that could be a little puzzle for you. How could attackers exploit the text you a code? Woohoo! Two-factor auth. Okay, that's a whole bunch of web security stuff, XSS, clickjacking, UI attacks, phishing, and defenses against phishing. We need a break. The break is long overdue. So let's take a 5-minute break and let's have some snacks. And then we'll come back in 5 minutes and do more web stuff. Okay, here goes. Back again. We have not exhausted the supply of web-related vulnerabilities. Thank you for staying with me. I know there's so much here. I love it so much though that I super get into showing it to you. So, and I know I'm sometimes a little slow. So thanks for sticking with me. All right, we talked about XSS and escaping as a defense. XSS happens because strings that contain both control, like markup, and data, like people's names. And we talked about UI attacks and phishing. And today, I want to, like for the rest of the lecture today, I want to show you SQL injection, command injection, and CAPTCHAs. And SQL injection and command injection are other types of vulnerabilities that we've seen prominently on the web, especially SQL injection. SQL injection is one of the top 10 most common. Well, it was as of maybe 5 years ago. Now the defenses, there's a lot of awareness, and I think the defenses are pretty effective, and so it's a lot less common now. But it's another instance of the pattern of injection vulnerabilities, which is an important pattern to know about because it crops up in a lot of places beyond just the ones I'm showing you here in this class. Okay, so background about how web services work. I get to give you a speed run through how websites are built in like, I don't know, 10 minutes or something like that. You really shouldn't learn from me. You should like take a real class or something, or like watch some videos, but here's the short version. A lot of websites have data like associated with your account, or their shopping, or there's settings or profile. They're like, your status pages and pictures you've uploaded. And the HTTP server, the core server, is stateless. It sees a request, it handles that request, given whatever information is in the request, and it's done with it. It doesn't remember anything. Except we need to remember some stuff because users are going to like upload photos, and those need to be remembered. So the usual architecture is that we have a database server, which is where all the stuff that needs to be saved across requests is stored. Like a user uploads a picture, that gets stored, let's say, in the database. Or changes profile settings, stored in the database. I enter in my birthday into Facebook, stored in the database. And then there is a web server that what it does is it receives a request, maybe does some database lookups to find any information needed to like figure out how to respond, maybe updates the database if this was like uploading a file or something, and then constructs some HTML response and sends the HTML response back to the client. And the web server doesn't have to remember anything across requests. Anything that needs to be remembered is stored in the database. So there's like a separation of concerns that enables web servers to be really scalable. And often a lot of requests don't change anything in the database. They just like read some stuff in the database. And so they can be very fast. They can be executed in parallel. If I requests they can have 100 copies of the web server, and they don't need to be synchronized. Just the database needs to be synchronized. And then there's this client, the web browser. This is in rendering these HTML pages and also running JavaScript. So there might be code running here on the web server, and then JavaScript code running in the browser, and the two are talking to each other. And the whole web application is built up out of these pieces. So what's in the database? Usually we use SQL databases, not always, but it's a common structure. And SQL database, if you've taken data 8, might be familiar. It's a tables data structure. Okay, so a table has rows and columns, and each column represents like an attribute, and each row represents like an item or an object or a thing or a person or a product that can be bought or something like that. And the database allows for like read operations, read stuff from the tables, find stuff in the tables, and then update the tables, insert into the tables, modify operations. And it provides all the synchronization necessary to make sure that if like you are modifying this table and I am modifying this table, that like our modifications don't mess each other up, and like waits until your modification is done and then does my modification conceptually, something like that. Okay. And the database makes sure that all the data is stored like persistently. So even if the server crashes, the data is still there, like makes reliability. SQL then is a way to, like a domain-specific language for fetching and changing data in these tables, and lets you specify what operations you want to do on the data in these tables. SQL is a declarative language where you specify what you want, and then the database figures out how to do that quickly. So the most common SQL command is select, and the select command, hopefully you've seen this in project 1. The select command allows a way to identify some data that you want to focus on. Like maybe only some of the columns, only some of the attributes are relevant. Ignore the other ones. You can also specify a where clause. So the basic select statement picks out a subset of the columns. You can also provide a where clause, which filters down to a subset of the rows. And the where clause can use any kind of expression to identify which rows to keep. Okay, so we can have a where clause, likes equals pancakes. That means in the likes column, the value pancakes appears. And that will pick out only rows that have the value pancakes in the likes column. So in this case, only that one row. So the result of select is another table that's been filtered. Columns and or rows have been filtered. And you can put any kind of like Boolean expression in there or combination of expressions. Update lets you modify the table. You pick out which rows you want to modify using a where clause, same as select. And then you pick a column and you specify what the new value to write into that column is, overwriting, replacing the previous value. So the selected, that happens then in every row that matches the where clause. Okay. So for instance, you could say in any row where the name is Willow, set the age to 6. You can delete rows. The where clause specifies which rows to delete. You can create tables. And when you create the table, you specify what the columns are and what type each one has. And you can also optionally, by default, it creates an empty table with no rows, but you can provide some data to go in. And then you can delete tables, use the drop command, not the delete. Delete deletes rows, drop deletes tables. And you can combine the results of these. Union, the results of a select is a table. If I have 2 selects, I get 2 tables, and I can combine them by union. That just like stacks them on top of each other as long as they're compatible. The union thing, you think of a table as a set of rows. So we're taking a set union of those 2 sets. So the top select gives me one table, the bottom select gives me another table, and then the union would be a result that has 2 rows. Okay. So the union is another way of doing it. I could have done this with select star from bots where name equals evanbot or mascot equals evanbot. 2 different ways to express the same thing. SQL has comments. They're denoted a little differently than other programming languages. In SQL, it's a dash dash, and then everything after that is a comment. And like, there's all sorts of other stuff in SQL. But hopefully that's enough of a primer. And I think you already had to use a bunch of this in your exploits in project 1. So now let's look at some vulnerable code and see how to exploit it. Here is code that might appear in a web server to handle a URL that starts with get items. And this URL has one parameter. Its value, its key is item, and the value is matcha. So this code that runs in response to this request The first thing the code does is it looks at all the parameters to look for one whose key is item and assigns that to this local variable. So with this example, the local variable item name will get assigned to matcha. Matcha is a string. And then this code will access the database by constructing a SQL command and sending the SQL command to the database. In this case, what this code is doing is it's trying to read part of the database. It's creating a select statement to identify rows in the database where the name attribute is equal to that parameter, in this case, matcha. And the result will be a table that comes back from this database. And then the code will continue to do stuff that might like include that table or display that table in the HTML response. Okay. So the query that executes if someone visits this URL is select from blah, 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 where name equals matcha. And matcha has been copied like directly byte for byte from the URL parameter by this code. Direct copying. Beware. Let's play around with some other item names and see what kind of database statement they would lead to. If someone types in the item name has a single quote, that gets copied into this SQL query with the single quote placed in instead of matcha being placed in. So now we end up with 3 quotes in a row. What is SQL data going to do when it gets this SQL command? What's the meaning of that? Any guesses? I haven't really told you enough to know, so you're just going to have to guess. What do you think it might be of something the database might do? Yeah?
Where the name column has
All right, that'd be a very reasonable thing. That's something a database might do if it parses by like, I guess we should think like a database as it's like reading in this query. How is it going to parse it? When it sees a single quote, it knows that's the start of a quoted string, and we should read up until the end quote. How do we know where the end quote is? If there's multiple more quotes to come, what are you thinking it might do? Okay, so what are you thinking will match on? It'll comma?
Like, I think it might take it from the rest of the code and like read that as part of the string or not.
No, it won't go from the rest of the code because this code computes a string and then sends that string to the database. And the string that's sent to the database is this. So the interpretation of the single quote stuff is done by the database, not by the code. So this code just constructs a string. It's just the string concatenation. There's nothing special happening in this code, and then send whatever the string you get to the database. The database has something where it tries to like interpret what this string means and separate, parse it, and so on. Good thought, yeah, but not. Any other possibilities? The %s is code that's running in the web server. The database doesn't know anything about that. The database just receives a SQL query, a string, and it interprets it. Doesn't care where it came from. So I don't know what the server's gonna do. I'm not sure. I think it might treat this as an empty string. Here's the beginning of the quoted string. Here's the ending of the quoted string, the middle one. And then that third single quote is like, I don't know what's happening here. It's the start of another quoted string maybe, but then I can't find a matching close quote. So what? This is not valid syntax error. I think maybe there's a syntax error here. And the SQL database will say, sorry, that's not proper syntax. You have a start of a quote, start of a string that isn't ended. I think, maybe, but it might depend on the database. Now I'm going to get fancy. You can see that one can put in here stuff that will be interpreted as part of the SQL command, not just part of the name to match against. So what I'm getting fancy now, I'm jumping ahead to the end. We could play around with this some more, but I'm jumping ahead to the end. I'm putting in is the value of this URL parameter, single quote, space, or space, some more stuff as shown on the slide. That's going to get copied byte for byte into the SQL query. The red identifies the part that was copied from the URL parameter. The black is hard-coded in the code. But we are the only ones who can see the color. Database doesn't actually get colors. The database just gets the string like without the colors. I put the colors in for our ease of understanding to understand which part was copied from where. But the database doesn't know what was copied from where. So when the database goes to parse this query, that query looks like the where clause says name equals empty string or 1 equals 1. So it's like a Boolean or of two conditions. Give me all the items that either their name is an empty string, probably none of them match that, or where this expression is true, 1 equals 1. The expression 1 equals 1 is always true, no matter what item you're looking at. So this is a query that when run against the database is going to match every row in this table and is going to output a copy of all the rows in that table. And then the code might proceed to do something like display that in the HTML response. So this code was intended to look up one item in the database and show it to the user. But if the user enters in this crazy string, they get to see the contents of the entire database. Probably not what the developer intended this code to do. Maybe not something the developer wanted to be easily accessible. Too bad this code allowed it. So by putting in these quotes and so on, the person who provided this URL parameter is able to provide some stuff that gets interpreted as part of the SQL statement, not just the name or the string literal, but also the affecting the control flow, the command. Yeah. What is the point of? The Boolean would be sufficient, but the black part, no matter what you put in the red, no matter what you put in the URL, the black part's always going to be here. So you can't like put some backspaces and erase the name equals. So the name equals is going to be there. So I need to like keep going from there. If this string was 1 equals 1, you'd have name equals 1 equals 1. It would like not do what I want. So I need to somehow like, it's starting with this name equals, and I need to like cancel that out and get back to like starting a new expression. So this is the way this is the hack. All right, so this is the project 1 hack. And it could be another thing that one could do is put in this URL parameter an end quote to kind of end this, get out of this quote context and get back into SQL commands. Put a semicolon, which allows starting a second SQL command, and then put a SQL command like drop table, delete this table. And then the SQL query that's executed will be interpreted as 2 SQL queries. First, the select that doesn't match anything, then drop table. What's the role of the dash dash and why would I put that there? Or what would happen if I left it out? Yeah. It's to comment out the apostrophe at the end. If this dash dash wasn't here, it would be drop table items and then a single quote, which a database is expecting to start a string, but there's no other matching quote that ends the string. So the database would say syntax error and not actually execute the drop table. But if it's in a comment, then it doesn't expect it to start a string. What would be another way, instead of using a comment, instead of using dash dash to avoid a syntax error? What could I replace the dash dash with? I'll help you. Semicolon. And then something. What? Yeah? Semicolon, then an apostrophe? Yeah, maybe it would like execute the select, execute the drop. Then it would see there's a third command that's two single quotes and be like, what? I don't know what to do with that. Maybe syntax error, but by then it's already deleted the table, quite plausibly. Or another thing I could put in there is semicolon, select star from items where name equals single quote. It won't match anything. It'll be harmless. It'll be a useless statement, but it'll be syntactically valid. Okay. Whew. So that's SQL injection. And what the attacker is doing is injecting SQL into queries that are constructed by the server. This might remind you of a vulnerability that we have talked about today. Which vulnerability we talked about today is this closest to? Yeah? To what? You said reflected XSS attack. Yes, reflected XSS attack. Totally, absolutely. An XSS involves injecting JavaScript into a string, or like HTML script tag in JavaScript. This involves injecting SQL into a string, or like SQL commands into a string. So it's the same vulnerability. It's injection. It occurs because string manipulation, string concatenation. The only difference is between the format of the resulting string is HTML or is it SQL? And the attacker, is the attacker putting in script, which is more HTML, or is the attacker putting in more SQL? It's the same vulnerability, totally the same. They're both injection vulnerabilities. Just one is injection into HTML, one is injection into SQL. Okay. So here's an example, a classic. You have to know this XKCD comic. First of all, if you don't know XKCD, oh, you're welcome. Go check it out. They're fun. It's fun. But if you do know XKCD, there's a classic XKCD that you have to know. Everybody, every security person who's ever heard of SQL injection knows this comic. So I have to teach you. I like morally obligated. I get fired if I don't. Yeah, you can read the joke for yourself. That's the mom. She's a hacker. In the XKCD, she's a like hacker, computer genius. Yeah. So I love it. Registering your name in the government database as a form that will like have a SQL injection to like check and see who's running, vulnerable code on their databases. Okay. And here's the other one that I'm morally obligated to show you. Totally a joke, meme, but here's how you spot the security researcher's car, because they hate speeding cameras. Oh, and so this was put in so that instead of getting a speeding ticket, the system that is detecting that they're exceeding the speed limit and registering their license plate and inserting it into a database of people to issue violations to will exploit a vulnerability in their code and like delete their database.
Nice. Like, does this have any relation?
No, this is ancient. This is like more than a decade. This is like 2 decades ago. I think it was somewhere in like, I don't know, Switzerland. What is? Yeah, I don't know. So maybe that was the name of the table in their database. I'm not sure. Yeah. Yeah, yeah. Yeah, this is attacking SQL. These are SQL commands. Absolutely. Yeah. It's kind of silliness, but you know, I have to show you. SQL injection vulnerabilities are like the cleverness of attackers is incredible. If you have a SQL injection vulnerability, you're in big trouble. You might think, you know, maybe I've got a SQL injection in my code, but I don't make public the code that I'm running on my website. No one's going to know. So who's going to know? No one's going to know. Well, it turns out that there is a technique called blind SQL injection that can be used even if you don't know what code is running or whether there's a SQL injection or not, to figure out whether the website is vulnerable to SQL injection, and if so, to exploit it without knowing anything about the code. And the idea is you first, well, anyway, is a tool. There's a tool that will do all this for you. And so this tool just scans a website, and if it has any, starts feeding in data to the URL parameters, and if it has any SQL injections, there's a good chance it'll find it. So what's the lesson I'm saying about that? I'm not really giving you details, but I'm kind of warning you that attacks get better, and attackers are smart, and they build up tools and infrastructure to help automate very sophisticated attacks. And there are these very sophisticated attack techniques. I'm not even telling you what the attack technique is, but I tell you it's super sophisticated, that would like you have to be really smart to come up with. But then someone implemented that as an open source tool, and now all the attackers can do this very clever thing by just running the tool without having to understand the clever method. So I'll tell you the clever method, but you don't need to know it. It's a tool called SQL Map. And what it does is it probes a website to find SQL injection vulnerabilities. And it just tries like finding every page and every URL parameter and like sticking stuff in there. And you can imagine how to do that based on your project one. It's like stick a single quote in and see if you get a syntax error when the page comes back. Except some websites might not give you a syntax error. It's not a very reliable method. So they have got a clever technique. Their technique, oh, it's so cool, is they, instead of just sending a single quote, they do a SQL injection that would, if it's vulnerable, cause a SQL command to execute. But they know that some pages won't respond with any error page or any visible response. So what they do is the SQL command that they inject is pause for 10 seconds. And they send this URL request. And if they immediately get a response, they know, okay, that was not a successful attack. But if they send this request and nothing happens for 10 seconds and then they get a response, they know my command to pause for 10 seconds just execute inside the database. I just found a SQL injection vulnerability. And then they can start replacing the pause for 10 seconds with stuff to like start trying to dump out the tables. How do you start dumping out what the tables are? We've got to know a table name to do a select. Well, you can like ask for the list of all tables. There's a default table name that has a list of all tables. So you can like ask for select for that table, except the response for that might not be included in the page that comes back. So they put some logic in there that says, if that list of all table names has a table name that starts with an A, pause for 10 seconds, otherwise don't. If it has one that starts with B, pause for 10 seconds, otherwise don't. Then try again. If it has one with a C, pause for 10 seconds, otherwise don't. And if you found a pause for 10 seconds when it starts with an A, now do it again, but see if there's one that starts with AA, see if there's one that starts with AB, see if there's one that starts with AC. So it totally automates this that would like works really reliably. Oh my gosh. So if you're vulnerable, attackers are probably going to be able to figure out and exploit it, even if you think this is a complete defeat of security through obscurity. So how do we defend against SQL injection? Actually, it's the same. It's the same vulnerability as XSS. It's the same defenses as XSS. Sanitization or escaping. So you can filter out special characters from the inputs. If I know this input is going to be used in a database query, single quotes are special. So remove all single quotes from the input before I use it to construct a SQL query. What's wrong with that? Why does that suck? I mean, it's okay, but it's kind of not great. Remove all single quotes from inputs that might be used for a database lookup. Will anyone care? Will anyone notice? Does it matter? Is that okay? I want to see if anyone else wants a chance to share some thoughts. It's okay if you don't, but I just want to give you a chance. Okay, what are you thinking? Removing single quotes altogether. Yeah, the problem is, what if I'm a user of this website and my last name is O'Malley? O''Malley. Then the single quote got removed and now this website has my name down incorrectly. So it might be a little annoying in some cases. Or I'm writing the great novel and typing it into this website and saving it there. And I'm using single quotes for showing what characters are saying. And then I write it all. And then I next day come to look at what I'd written and all the quotation marks are gone. So that's a little unfortunate. So a better defense is, just like we do with HTML, to escape. Take all those special characters and replace them with something that we're confident will not be treated by SQL database as special, as like ending a quoted string or being part of a SQL command. They can will only be treated by the SQL database as content, as data. And SQL has a way to do that. It lets you use / single quote. And then it promises, I will not treat this as a string delimiter. I'll just treat this as like a character that can occur in a string. And it doesn't end a quoted string or start one. So you can escape data before inserting it into a SQL command. Use a library to do this because it's tricky to know what all the special characters are. A plausible defense. What's wrong with this defense? I'm asking you an easy question now. We talked about what's wrong with this for HTML, for XSS. It's the same thing that's wrong with this for SQL injection. What's wrong with escaping? It's a plausible defense, but it has a shortcoming. I know it was like an hour ago or 2. What was the shortcoming of escaping for XSS? Yeah? Oh, I'm so sorry. The fans are so loud over here. I got to come a little closer. Can you just give it to me one more time? Yeah, sometimes people forget to put this call to the escaping function. Because it's one of those things where I have to, the default is unsafe. I have to remember to do something extra every single time. Bad design from a human factors perspective. Yeah. So if there's 100 places in the code where SQL commands get constructed and 99 of those places developers remember to escape, and one of them some developer just plumb forgot, maybe no one will notice. The code will seem to work correctly, but it'll actually be vulnerable. Yeah, so the default is unsafe, and we'd rather have a default be safe. So how did we resolve that issue with XSS? How did we come up with a better way to structure web applications so they were default safe against XSS? Yeah? Templates. So the answer here is the same. Templates. So a better way is to use templates, use a template system for SQL queries, where your template specifies the SQL that has a hole, and use some library to fill in the value at runtime of what that hole, what to put in that hole. And the library is responsible for always escaping. If I always use the template system, I never use string concatenation, then I'm safe. And for whatever reason, with SQL databases, they have a different name for it. Yay, computer science, we love having names. We have 100 names, way more names than we need. We should just call it templates, but we don't. We call them prepared statements. And it's just a template. And the way this template works, you can see down here a template with a question mark. That question mark is a hole to be filled in at runtime. It's just like with HTML templates where they had the curly brackets for the stuff to be filled in later. In the SQL templates, you put a question mark for the stuff to be filled in later. Except if you go tell anyone else outside of this classroom that you use templates to protect against SQL injection, they're gonna be like, what? What are you talking about, dude? The standard name is prepared statements. So you instead say, I use prepared statements to defend against SQL injection. And I'll say, way to go, good solution. So this is the standard solution to defend against SQL injection. Never use string concatenation or combine strings together. It's the combining strings together that gets trouble. Use prepared statements template system. And then this is default safe as long as you do that. So this defense has basically eliminated SQL injection in essentially all websites made by anyone competent, because everyone competent knows you use prepared statements to add in dynamic values, not string concatenation. Okay, so that is SQL injection. It's an injection vulnerability. Hopefully you've seen two patterns of injection vulnerability, so you can now guess why I'm showing you this. You can have injection vulnerabilities in any text format if the program tries to insert data into that text format at runtime and is not super careful about how it does so. So you now know how to create about 10 more vulnerability classes. Pick your favorite text data format, add the word injection, and you've got a vulnerability class. JSON injection, woohoo. Markdown injection, woohoo. I don't know, YAML file injection, boom, you got another vulnerability, let's go. Fire up that blog post. And here's one more, command injection. So this is shell commands. In a command injection, it's the same vulnerability, except instead of HTML, instead of SQL queries, we now have shell commands. And some programs will start a new program running by like constructing a shell command and then running that shell command. And if you're not careful about how you fill in values at runtime into that shell command, you can end up with a command injection vulnerability. Okay, so in C, there is a library function called system. You pass it a string, it interprets that as a command line, a shell command line in your like terminal, and it runs it, just like if you typed it into the terminal window. Most languages have a library function to do that. It might be called system, it might be called something else. Okay. So here's an example of vulnerable code that's vulnerable to command injection. This code is like trying to implement some like company's database phone lookup, phone number lookup. And someone's going to use this application by providing an employee name, and it's going to look up in their phone book for the user with that name, and it's done in this really crude way. There's a text file with one line per employee with their name and their phone number, and this was like super like coded up really fast. I don't know, vibe coded or something. Let's just call the grep command. The grep command like searches for a line that matches that contains as a substring the employee name. Okay, so this constructs a grep command at runtime, fills in that %s gets filled in with the employee name. And then when you run grep, it should like find the line in that text file with that name. Okay. So if the parameter is dashwood, then it constructs the shell command grep dashwood phonebook.txt. Whatever is put in this parameter is blindly copied in here. String manipulation, blindly copied into text format, boom, injection vulnerability. What's an example attack? If the attacker can specify their own name to look up, they could specify this crazy name here. It's got single quotes, it's got semicolons, it's got shell commands. Oh my, it's full of stars. And what'll happen when this gets placed together into the string stuff is we'll have grep single quote from the source code and then a single quote from this parameter and then a semicolon, and the grep now does kind of nothing. And then a shell command to send email to the attacker with a copy of this sensitive file. And then something more to like ensure this is not there's no syntax error. And now when this is run, it'll run all three commands, and now the system is not just running grep on some to search for some string, but it's running any command that the attacker wants. So the attacker now has like root access or, you know, shell access to that machine. Okay. So it's injection. How do we defend against injection? The same defenses. You use sanitization of inputs, filter the inputs to remove special characters. Any character that might be interpreted by the shell to like end the quoted string or get treated as part of a shell command. Or, well, that's annoying to do because I can't search for the name O'Malley with an apostrophe in it. So better is escaping, output escaping. So you escape all the special characters in a way that the shell will not interpret as special character, but will just interpret as content. And the shell says you can do that by putting a backslash, except the shell has so many crazy special characters that you really don't want to try to do this because you'll never figure all of them out, and it's likely that you'll never get that right. So actually, for command injection, the format is just too complicated. Don't even mess with output escaping. Painful. Instead, what is better is to use something that's kind of akin to templates. Except instead of using templates, don't use an API where you pass a string that contains an entire command. Use an API where you pass like array, where one is the program and then array of the arguments, and fill in one of the argument values dynamically. And crucially, then use an API that doesn't interpret this as a shell command, but that just calls the program directly with those arguments. So basically, use pre-parsed commands rather than strings. Okay. That's injection vulnerabilities. So I want you to know about injection vulnerabilities, both the common ones, but also to just recognize when this pattern could come up in other data formats. And then the last thing I want to show you about is CAPTCHAs. Just something has nothing to do with everything else we've talked about, but it has to do with web security, something you might run across on the web. If you've ever hit one of these on the web, or please click all the grid squares that contain cars, that's a CAPTCHA. What's the purpose of a CAPTCHA? The CAPTCHA is designed to make sure that a website is usable by humans, but prevent automation, bots from accessing the website. For instance, LinkedIn loves to use CAPTCHAs because they want me to be able to go there and like try to match up with a recruiter. That's great, that's what they're designed for. But they don't want a recruiter to be able to run a script that goes and downloads everybody's profiles of 1,000 people that match some condition and whatever. Why don't they want recruiters to do that? Because they have a separate paid access. Pay them $500 a month and they'll give you a way to do that. They don't want you to run a script and be able to do that for free. Okay, so they want to detect which requests are coming from bots and block them. And the way they do that is they provide this CAPTCHA, which is a puzzle that should be easy for a human to answer, but hard for a script or a bot or a program to automatically answer. So that's what a CAPTCHA is, a puzzle that hopefully humans can answer and that bots cannot easily answer. And there's lots of them. Can be super annoying. Maybe you run into some of these where there's like distorted words and you have to figure out what the letters are despite the distortion. For people who are blind actually, or have sight impairment, CAPTCHAs are a real problem because you can't use a website if you can't see to answer the CAPTCHA, you're just blocked. So most websites will provide an alternative, the little tiny link that says audio or something like that. I suggest, if you're ever curious, to try clicking that audio link and see if you can get through the audio CAPTCHA, like with your eyes closed. You'll hear just some distorted voice, like 3497, and you're supposed to type in like 3497. But some of them are really distorted, and it can be really like hard to figure out how to pass the CAPTCHA. Okay, simple technique. Increases the cost of building a bot. Makes it hard to build a bot that uses the website because the bot's going to get blocked by these. It can't answer them. But it's easy for human. It's like common sense stuff that we can do in our sleep in just a moment. A little annoying for people, but doable. That's the basic concept. Google introduced this system called reCAPTCHA that has this really clever idea. And the clever idea is while you're solving the CAPTCHA, how about we repurpose the time you're spending to also do something valuable? So what they'll do is they'll show you an image and they'll say, click on all grid squares that contain a motorcycle. Half of the time when they show you this, they know the answer, which grid squares contain a motorcycle, and they're checking to make sure you click the right ones. And if you don't click the right ones, you're a bot, you're blocked. The other half the time don't know the right answer. They're trying to come up with training data to train machine learning algorithms, but it costs money to hire humans to like annotate where the motorcycles are. So instead, they've made this CAPTCHA. So you, using their website, their free website, are providing a little bit of labor to tell them where the motorcycle is. So half the time, they don't know the right answer, and they'll just accept anything you click. Except that's not really okay, because who knows whether the answers that people are giving you in those times are correct. So what they'll actually do is they'll show that to two different users, and they'll check if both of them match, and kind of as a quality control or do stuff like that. So they have variations on this idea so that when you're solving a CAPTCHA, you're doing a tiny unit of little useful work that's useful to Google. Some of the time, and the other some of the time, you're proving you're not a bot. And that's enough that half the time you're proving you're not a bot, because a bot that just answers randomly might be able to get through one of these, and then the next one will be the real test, and it won't get through that, and it'll be very quickly blocked. The bot won't be able to get very far. Yeah. Google provides a service called reCAPTCHA that any website can use if they want a CAPTCHA service for free. That's why they do it for free. So it's cool. Websites that want a CAPTCHA, they just load that JavaScript library. They've got a CAPTCHA. They doesn't have to pay anything. It's cool for Google. They got a little bit of data for their machine learning algorithms. Now their machine learning gets better at tagging motorcycles or cars or whatever in their image recognition. It's just annoying for people. Oh, well, you weren't the customer anyway. You were the product. All right, so the problems with CAPTCHAs are, one problem is that as computer algorithms get smarter, CAPTCHAs need to get harder, which makes it harder for humans to solve. And we're sort of at the point where there's an overlap between where the capabilities of the least capable user, human, and the capabilities of the smartest bot. The smartest bot can solve harder CAPTCHAs than people can. And so you end up with CAPTCHAs that either some humans can't solve and you're blocking real humans, or CAPTCHAs that some bots can solve and you're not stopping the bots. And another problem with CAPTCHAs is outsourcing. People who want to run bots can hire people in third world countries where their pay rate is really low in sweatshops to work for peanuts, solving CAPTCHAs all day long, getting paid $5 an hour, solving 1,000 CAPTCHAs an hour, and now it costs, you know, like half a cent per CAPTCHA for the bot to solve. And so there's underground markets that will solve these for a price. So this increases the cost of running a bot a little, but it doesn't prevent it. Thank you so much for your patience with me today. I wanted to show you injection attacks, especially SQL injection is a crucial one, but also command injection, and to see the general pattern of injection. And hopefully you now have a little better understanding of what those crazy puzzles that you get hit with on websites called CAPTCHAs. Thank you. I'll see you next week.